Hello guys, so we are saying I'm introducing these concepts on the Kirchhoff's rule and voltage rule and the Kirchhoff's current law. Okay, so for this video, I'm restricting this video specifically to ordinary differential equations. For those, I'm preparing the concept on application on ordinary differential equations on the electrical circuits. Okay, so we are saying for you to understand the electrical circuits, our first step is to understand the Kirchhoff's rules, voltage law and Kirchhoff's uh, current law. So for this video, I'm restricting it to ordinary differential equations. And again, maybe check my playlist on elements of physics, the fundamentals of physics. You'll get to understand more on these lessons. So we are saying we have the Kirchhoff's rule. So our first step, we are saying, suppose we start at any point. So we'll be calculating the current in a single loop in a single loop circuit based on the concept on potential. Okay, so we can calculate that again. We can calculate the current in a single loop circuit based on the concept on energy conservation. Okay, so we are saying suppose we start at any point in a circuit and proceed around the circuit in either direction. That is it can be either clockwise, okay, can be clockwise or maybe anti-clockwise, okay, anti-clockwise. So we are saying if we go in either directions, the algebraic, okay, while we are adding the algebraically the potential difference that we encounter and return to the starting point, we must also have returned to our starting potential. Okay, so we are saying our first step is to understand what Kirchhoff's rule, loop rule, which is Kirchhoff's voltage law. It states that the algebraic sum of the changes in the potential encountered in a complete transversal of any loop of a circuit must be equal to 0. Okay, so let's get this. We'll use an example to illustrate that. So we're saying let's go straight toward the resistance rule, which is for a move through a resistor in the direction of the current, the change in the potential is negative IR. Okay, so if we move uh, through a resistor, but now the direction of the current is in the opposite direction, we should get the change in potential as becoming positive. Okay, so we're saying let's go to the EMF rule. We are saying for a move through an ideal EMF device, the direction of the EMF arrow, okay, uh, the change in the direction of the EMF arrow, the change in the potential should be positive. So if it's in the opposite direction, the current is in the opposite direction with the EMF arrow should be negative. So for this case, we are saying example. So we are saying example. So we are given this circuit, okay? So given this circuit and we are told let's calculate the current inside this circuit, okay? Let's find the expression of the current through this circuit, okay? So our first step is to start at a certain potential, of which for me will start from this VA, which is at a lower potential, okay? So it's at a lower potential. We start from here, then we'll transverse this loop of circuit in the clockwise direction. Okay, we'll transverse this in the clockwise direction. So we are saying if we move from VA, then we go in the clockwise direction and come back at VA, we should get our starting potential. And all the changes in this circuit, all the potential changes in this circuit should equal 0. So if we start from VA, okay, so you start from V and remember VA is at lower potential. Why? This is because it's in the negative terminal of the battery, okay? So this battery doesn't have an internal resistance because this is an ideal battery, okay? This is an ideal battery. So if we were having a real battery, we should have included the concept on internal resistance. So that is negative IR, okay? But for this case, we are dealing with an ideal battery. So for an ideal battery, we shouldn't include the internal resistance. So it means the potential at B negative should equal the potential across the terminals are equal. Okay, so we are saying if we move from VA, then we are saying using the EMF rule, we are saying for a move through an ideal EMF device, which is our case, the battery, in the direction of the EMF arrow. So the direction of the EMF arrow is in the positive upward direction. Okay, so we are saying the current also is moving from the negative from the positive terminal up. Okay, so the current again is moving in that direction. So we are saying if the current is in the direction with the EMF arrow, we are saying the change in the potential at that point should be positive. So I'll add that as E1. Okay, should be positive. And again, we are saying, let's continue. So already we have reached at this point. So I'll explain another concept which we are saying, along the wires, we don't have any potential difference. So the potential uh, is zero at any wire, at any length of the wire. Okay, so once we have reached at this point, so the current I enters through the resistor. So we'll use the resistance rule, which says for a move through a resistor, so we are moving through a resistor in the direction, okay, in the direction of the current. Okay, so we are moving through this resistor in the direction of this current. We should get our potential as negative IR. Okay, so we're saying at this point should be negative IR. So we'll equate that. So we are saying we should come back to our starting potential. Okay, we should come back to our starting potential. So all these traversal changes, these algebraic summation, we should come to our starting potential, which is V of A. Okay, so from this point, let let's take VA to this other side. So let's transpose this to this other side. We'll get VA minus VA, which will equal to 0. So we are saying E1 minus IR equal 0. Okay, so we are saying E equal IR. Okay, so for us to get the current through the circuit, we'll divide by R and divide by R. So we should get E upon R. So we are saying the current through this loop of circuit, we are saying it's the potential of the battery. Okay, the total potential voltage, the total voltage of the battery divided by the resistance through the circuit, the total resistance in the circuit. If we do that in the counterclockwise direction, okay, in the counterclockwise direction, we see we are coming to the same. So we are saying VA. So we are going in the counterclockwise direction. Okay, counterclockwise. So if we go to the counterclockwise direction, we are saying along the wires we don't have any change in potential. So if we are going, the current is going against the resistance, we should get a positive IR. Okay, so we should minus that as we go into this side. So the current is against the EMF arrow, so it should be negative. So it should be negative E1. Okay, negative E1. So, and remember, keep in mind this should be epsilon. Okay, should equal VA, the starting potential. So if we transpose this, we'll get IR equal E1. Okay, so we're saying for us to get the current, we'll get E1 divided by R. So as you can see, if we go either way, okay, as the statement says, we are saying either direction we should get the same answer. Okay, so for this video I'm explaining this concept in relation to ordinary differential equation. So there's a point where we'll come and derive the expression for the RL circuit and the RC circuits, okay, for the first order differential equations. Then we'll use again the Kirchhoff's voltage and current law to derive the expression for the RLC circuits in applications of first order differential and second order differential equations in electrical circuits. So please like, share, and subscribe to my channel. Thank you.